Hi, everyone. I'm Alex Levinson. I'm, as stated, a principal algorithms engineer at Elbit Systems of America. I specialize in tracking systems. So my background before I was at Elbit, I worked at Raytheon in the defense industry and was briefly a VP at a startup here locally in Miami. But now I like to stay in the realm of tracking systems and algorithm development. So here I am. I also, I'm graduated from the University of Florida, so yep. Yay, go Gators. Okay. So what is video object tracking? Tracking is the process of basically monitoring an object throughout a video frame. So what that means is you want to localize that object, and then you want to be able to predict the trajectory of that object so you know where it's going to be at the next frame. There are different categories of video object tracking. You could do multi-object trackers, single object trackers, online or offline, basically if your models are pre-trained or if it's going on the fly. And detection-based and detection-free, and I'll get a little bit more into that later. Some industry examples. So self-driving cars is the biggest one. I work in defense, so my job looks a little bit like the video you're seeing there, where it's more of tracking aircraft, stuff like that. But there's also a lot of opportunities in medical imaging and robotics, even like sports analytics. There's a lot of different applications for video object tracking. A tracker has two main components, typically. The detection component, and that has an appearance model and takes advantage, so that leverages spatial features. The detection models work frame by frame, and then you have the object motion model, which will tie those frames together so you can predict where that detection that you localized on the individual frame will actually be on the next frame and the following frames. Some of the main challenges in tracking are occlusion. So that's if you're tracking an object and either the two objects get very close to each other, or if it goes behind some other structure or something and you lose your actual detections, you'll still have a track on that object because you're predicting the trajectory, but you won't be able to actually see that object. So when you can see it again, you need to be able to accurately pair the track that you had with the trajectory to the detection that represents that specific object. A lot of tracking systems are sensitive to appearance and scale changes, which is one of the main reasons why we use deep learning now in the tracking field, because it adds an extra layer that augments pre-existing tracking methods. And as you may know, deep learning models are very computationally expensive. So to get those working at real-time frame rate is usually 30 frames per second, something like that, 60 frames per second. So you want these to be running pretty fast. They have to be pretty lightweight. And especially if it's on something like a self-driving car or an aircraft, you can't have so much hardware on it because with the weight. So that's definitely a challenge that needs to be mitigated. So as I mentioned, one of the largest applications just in the commercial sector is self-driving cars. This is a GIF from a video from NVIDIA, actually, and this shows some of their driverless car technology right now. Those boxes that you see on the bottom are track boxes, and the numbers that you see right over them are unique object indicators. So that's usually a tracked object is assigned a bounding box, and that is also assigned a unique object indicator, which helps you from frame to frame across the video sequence keep track of what that is and save off some information about it. One small difference with this video versus some of the methods that I'm going to talk about, this is a mask method. It's a segmentation method. So every single picture in the frame has been identified. The outputs of the systems that I'm going to talk about later are just the bounding track box. So this is your object and you're following it. Okay. So the general method of a tracker is it has 4 main components. It has the object localization or detection component, which basically, for a classical tracker system, we're going to assume that it has a detector. I'll get into one that doesn't have a detector. But it has, this detector basically says, this is, I think, the object of interest, this, or at least this is where it may be. If you, some of the newer detectors, like an algorithm called YOLO, which I'll talk about, that is actually tied with a classifier. So you'll be able to localize the object and classify it at the same time. The second component, so you have the detection, and then you use that detection, your blob of interest, to instantiate your track. Your track is where you're going to be estimating your trajectory of your object. And the 2 main ways you can do that are by measurement dynamic models like a Kalman filter. Kalman filters are really widely used everywhere in trackers. They actually, I think it was developed for Apollo mission, so it's been used for a long time. But some new methodology is, there's deep learning methods that you can also use to predict the trajectory of objects. Typically, computer vision deep learning methods are kind of more on the detector side, so that's a pretty novel advancement. And the specific neural network that is used in this context is an LSTM network, long short-term memory, if anyone is familiar. So once you have your detection object, you have your track, you need to know how they go together, basically. So there's an association algorithm component that allows you to calculate the similarity of your detections and your tracks and pair it together so you can update your track estimates with your information that you're going to get from your detection frame. At this point, assuming that the track information is up until the last frame, your detection frame is your current frame, so you update that so you can keep going forward with your predictions. And then, yeah, the output of that is to get your consistent identity label. You want to know that car number 1 is car number 1 from frame 1 to the end of the video sequence. And then there's a track maintenance step where basically if you're tracking an object, you don't get detections on it for a certain amount of time, you might want to do something like delete that track or downgrade it from its trustworthiness score. So the current state-of-the-art tracking method, that's not deep learning. And the reason I'm starting here is because it gives you a really good understanding of a lot of the components within a tracker, and then the deep learning methods build onto it. So this current state-of-the-art is called SORT. It's a simple online real-time tracker. This is a multiple object tracker. It works in real time, as stated, at frame rate. And so this is, because it doesn't have the deep learning step, this one is going to be specifically very sensitive to things like occlusions and scale changes. The good thing about this algorithm is it's a very, very lightweight. So you can use something for your detection step, which is the first step. You can use something like a CNN or convolutional neural network-based detection algorithm. It still has to be one of the more lightweight ones, but you can use that with the rest of the algorithm and still have it running at frame rate. The most commonly used detection algorithm is, like I said, that YOLO algorithm. The reason why that one is used over some other ones is It stands for you only look once. So if how other convolutional neural networks work, there's a sliding window, which basically means you have to pass over the image something like 2,000 times. This, you only pass over it once, so you save a lot of resource consumption that way. So once you have the detection and you instantiate your track based off the detection, you'll have that box from the detection. Then there's the estimation step with a common filter, and that takes in your position state, your velocity state, does some dynamic modeling, updates measurements. There's different noise models that are included into it as well. And that allows you to recursively estimate what your position is going to be on your current frame. So after you have your tracks updated, your detections updated, then there's that association step. The common method that's used with that is the Hungarian method, and that's essentially just a cost minimization algorithm that uses the Mulholland-Obis distance as its metric that it's minimizing to. The reason why that's used is because everything coming out of the Kalman filter is a distribution, so Mulholland-Obis distance accounts for distributions, as opposed to something like Euclidean distance, which is just going to be for a single number. Yeah, and then there's that track maintenance step. So you're gonna have counters on things like track age, the association history, so what detections it's been associated to, how many frames you've seen it for, how many frames you haven't had detections on it, stuff like that. And that can be used cleverly in order to upgrade or downgrade tracks to get to the object that you want to get to. That image is a clip of a sort tracker. And you can see that when they cross over, there's that wedge that forms. And that wedge actually indicates that you're searching for detections in that general area. So when they cross or there's an occlusion, you have ambiguous detections and you lose that information. So this algorithm is sensitive to that. And the way we fix that sensitivity is with deep learning. So the first deep learning algorithm is DeepSORT. Essentially that sort algorithm with an additional appearance feature vector. So what that means is that distance that I was speaking about, the Mulholland-Obis distance, that's minimized between what your detection state looks like and what your track state looks like, that number is actually augmented with the appearance vector. So how that's done is you take a convolutional neural network, a classifier, and then you strip off the final layer. It's called transfer learning. You strip off the final layer and you can develop a feature vector from that. And then you have a feature vector of what it looked like before it went out of frame or was occluded. And then you can use a cosine distance to assess a similarity of that. And that will help with your detection and track association. And that is DeepSORT using the YOLO v4 detector. You can see that even when some of the people cross each other or go behind some areas, there's still pretty good track consistency there. So this method is, we're moving away from Kalman filtering and getting kind of purely into the deep learning area. This is recurrent YOLO, so ROLO. And ROLO, this is a very new method. It's also, by the way, it's open source, so if you're interested. But this is a single object tracker version of YOLO that uses an LSTM network as the motion model. So you're not using a Kalman filter anymore. Now you're taking a YOLO detector, and the outputs of that YOLO detector are going straight into that LSTM model. And that gives a very good performance against things like occlusion. You can track object, that's an unseen sequence in that video, so you can really easily track unseen objects. It doesn't have to be trained in too specific of a way. It's pretty generalizable. And the output of this as well is that bounding box. So the red box there is the ground truth. The blue box, it's changing pretty significantly in size frame to frame. That's actually a detection box, so that's kind of expected. That may be different frame to frame. But that green box is your track that you're getting out of ROLO. And you can see that all of the different scale and appearance changes for that surfer, he's still being pretty consistently tracked. And this is again, on an unseen data. The reason why LSTM is used is because it's good at learning historical motion patterns specifically. It's not just feet forward, there's a feedback step as well. So that's a good computationally inexpensive way of having a deep learning method to learn the trajectory. Okay, this one's a little bit different. This one's called GOTURN. This is a detection-free network. And what that means is that we don't use something like a convolutional neural network to give us kind of like a proposal of where our object may be. This network is actually trained using labeled tracking data. So the inputs to GOTURN when you're training it are your current frame and one frame before and the track boxes of those frames. And using that position delta, it can compute where the logical position is for the next frame of that specific object. So this is a really fast way of using deep learning for object tracking. It's available in OpenCV, so it's like fast in when you're actually coding it and implementing it. It also runs up to 100 frames per second. So just for context, that YOLO algorithm runs at somewhere around like 45 frames per second, so this is pretty fast. It does generalize well to unseen data like the other methods, but one of the issues with this is it's really, really dependent on your training data because it's an offline network. It's pre-trained. You're just taking those weights and putting them into whatever system you're using for deployment. So, so it's really going to be very subject to how you're training it. And then some of the specifics, it uses L1 loss, and yeah, the output is the bounding box coordinates again. So that video, you can actually see, I think that's in OpenCV. Someone was doing a demo, but you can see that they're selecting manually that detection object, and then all the subsequent frames, it's tracked. Okay, so some closing remarks. So there are so many detection methods and a lot of tracking methods. This is just a few of them. You can use different detection model inputs to a tracker. So I'm assuming object detection for simplicity, but you can actually have a full classifier input to a tracker, or you can have a full masked segmented model input to a tracker as well. So video object tracking, I used video sensors for the information, but you can also use IR, radar, LiDAR, whatever sensors that you may need. And yeah, there are a lot of available benchmarks and data sets out there to assess your tracking performance in a standardized way. So that's available. And yeah, it's a dynamic and developing field. It's really fun to work in. So I encourage anyone who's interested to look on GitHub and see what's out there, because it's very cool. By the way, that video is on one of the benchmarks that I mentioned, the Mach 20 data set. But, yep. Thank you.
LSTMs for tracking and whatnot, and I get that because they're really big for time series prediction and natural language processing. Has there been a shift towards transformers or kind of other more state-of-the-art deep learning techniques that might phase out LSTMs, do you think, for tracking?
Yeah, so I've seen recently like Siamese networks and autoencoders being used pretty frequently. That's more for, it has more of a specific application. So I was kind of focusing on multi-object tracking because it's kind of the easiest to understand. But if you want to do a really, really precise single object tracker, a Siamese network is one of the good ones. It's that's all open source too. It's called SiamNet. So
Awesome. Thank you.
You're welcome.
Thank you. I think a big question around this tech is the affordability. Now I'm in the cruise industry, and sometimes things do happen in what we call man-on-board scenarios, where we do have a way to identify if there was an accident. But then it's all tied to having a good quality CCTV camera, and the actual model is complex. And there are things available, but which are like super expensive. So do you see this getting affordable? And
it is pretty affordable already. So you can go, there's a spectrum of how you can implement it. I myself have implemented on like a Raspberry Pi with a PS3i camera. That's pretty inexpensive. Total, it's like $200. You can also go all the way up, and that might not be the best application. I'm just saying that it starts there. So you can go all the way up to the most cutting edge processors, and of course, it's going to be dependent on the cost of GPUs and stuff like that. But you can do a surprising amount with some pretty lightweight cameras and some pretty lightweight processing. It's really what you need from what you're doing. I do see it being affordable, as especially as the GPUs get a little more inexpensive. So.
Great presentation, thank you. Just to clarify, the examples you showed, were they frames or pictures predicting tracking to the very next frame, correct? Each one of those examples?
Yeah.
Okay.
Yeah. So how it's done? Well, it's recursive. So you're predicting based off of your last frame's measurements what you're going to be on your current frame.
Got it.
And then you have your detection measurements. You're associating that together.
So what if the use case, and I'm just curious, if the use case was, I either want to know in X number of frames past where the object is going to be, or at what point in time, based upon the trajectory, the object will be at X seconds, whatever. Can the same techniques be used, or is the computation different, just out of curiosity?
Yeah. The same techniques can be used. So Kalman filter is actually pretty good for that. The Kalman filter is pretty modular in the way that you can choose the amount of states that you want to put in it. So if you put something like an acceleration state and not just a constant velocity state where it's just going one direction, then you'll actually be able to get a pretty accurate prediction on where you're going to go. One of the uses for that here is, I mentioned the occlusion. So when you get detection dropouts and you have a track, you kind of don't know where to tie it to. You only have the predicted states. You don't really know where to tie it to kind of reinforce that measurement that you get. So if you have good models that can accurately predict where you're going to be in a couple frames, then you have to grow your uncertainty a bit, so you increase your search area. But that'll give you a pretty good idea of what's going to happen, so that you can correlate your detections back to your track.
Thank you so much.
Yeah.
Thank you. Comparing the first model that you show us, the SORT model, against the SORT model seems more an ensemble model of deep learning and geometrical model, and the other one that is ROLO, GOTURN, is more an end-to-end deep learning method. I mean, if you compare both of them in performance, when to use one, when to use the other approach, or they perform in the same way? How do you compare that?
Sure. So the SORT algorithm, that's used for like a general multi-object tracking scenario. So you have, let's say you want to track traffic and you have a bunch of cars and you want to track every car. You could use something like SORT or like DeepSORT for that specific scenario. ROLO is a single object tracker. So that means that you're not going to be able to estimate trajectories of multiple objects in the scene. You kind of have to stick to your one most interesting object. And then both of those are online trackers. So they're not like pre-trained networks or anything. The only pre-trained part of that is the actual detection component, the YOLO algorithm, but that's separate. So for the tracker itself, yeah, those are going to be online. GOTURN is also a single object tracker. So if you have a bunch of objects in the scene, you only get your one object. That's a pre-trained network. So that means that you only have your weights. It's not good that it's not going to be dynamically updating in as you're using it. So it kind of depends on what you need. If you need something that's going to be really, really fast and generalizable and track one object, GOTURN is the obvious choice. If you need something that has a little bit more flexibility and you can kind of add in components, SORT or DeepSORT would be really good for that. ROLO is really good for like a super accurate single object tracker that's online. And yeah, just depends on your use case.
Hi, can you hear me? Hi, how are you?
Good, how are you?
Doing fine, thanks. Looking at one of your earlier examples, assuming that you work with the military a lot, I noticed that one of the object was almost off the screen before it was detected. So just the question is, how heavily weighted is time, detection time or time in the models, or just in terms of like user requirements, business requirements?
Can you repeat that last part again?
So I was noticing that one of your earlier examples, that the object was almost off the screen before it was detected. So I was just curious of how heavily weighted is time. Does that make sense? Yeah. I was noticing one of, I don't know if you can go back, but one of your earlier examples.
You tell me when to stop, I'll stop.
I'll tell you, keep going. When you're with the cars, it's right after the aircraft.
Gotcha.
Okay, yeah. And the second example, you noticed that car number 9 was almost off the screen before it was detected?
Yeah.
So just curious if that's right there.
Yeah, I mean, if something's flying really fast, there's
Right.
it's difficult. That's a corner case. How I think the best way to mitigate that is maybe not necessarily with a tracking system,
Right.
but with some kind of like, I'm blanking on the word, like a gyro. So basically you can, a gimbal system, so you can keep looking at the objects that you're interested in.
Mm-hmm.
So ideally in that case, and this gets more into like systems design, but ideally in that case, if you're looking at your object that you're interested in, or at least in your area that you're interested in, you should be able to detect objects fast enough. And if you get an object that can't be detected until the very end, sometimes that can
Gotcha. That makes
cause-
sense.
Yeah.
Yeah, the basis of my question is I'm former military, and I remember having to do stuff like this manually. So
Yeah.
I figured if you're working with the military, that would be one of their questions in terms of time frame, right? Like
Yeah.
how fast you can detect these images. That's the basis of my question.
Yeah, so I believe this one is working at 45 frames per second, so that's fast. Another thing that you can do is kind of like a step stair pattern. So you increase, so if your camera can't see, if it has a relatively low field of view, narrow field of view, you can increase the field of view by looking in different areas strategically. So if something is flying off the screen or something like that, hopefully you'll already have step stared to that point where you'll have previous information and you can kind of correlate that to a track where that's called a field of regard. You just be increasing the area that you're looking at. But as far as detecting something faster, that if it's on the edge, that's a difficult case.
So for an underwater vehicle or any other kind of like robotics platforms that uses vision, what type of lightweight algorithm would you recommend using?
For an underwater,
Well,
what's your sensor?
well, we're using like a camera, for example, and I don't actually know any other sensors that are going to be used with it yet. But like, I just want to know like, what would be like a lightweight kind of like use, I guess, for like. I was originally thinking of like using YOLO, for example, but I just wanted to know like your opinion on it.
Yeah, so I would use the YOLO detector. It's probably gonna be the fastest. Second one you might wanna try is an SSD detector. It's pretty similar to YOLO. And then I'm partial to a Kalman filter. I know it's not deep learning method, but I am partial to a Kalman filter. I think it's really tried and true. So if you wanna take your YOLO detector and use that with a Kalman filter for the track to detection associations, because YOLO isn't going to give you tracks, it's only going to give you detections. That could be a really good place to start.
Thank you.
Yeah, when you train these kind of algorithms, you use GPUs. Do we still use it like in our personal machine, or do we invest in servers, Amazon? What's the best practice today?
Depends on how big your neural net is, but you can get really far. I use a gaming computer, so I have my own personal laptop. You can also use any of the the NVIDIA like Nanos or Jetsons, things like that if you want like a separate board to do development on. Those work.
Hi, so for the recurrent YOLO, does it require like a lot more computing capacity in terms of GPU processing, or that compared to the, I guess, the previous just standard YOLO? So the recurrent YOLO is the LSTM, correct?
Yeah.
So is it like 2 times, 3 times more processing power needed for that?
So I don't have the exact number, but so they both need the YOLO detection algorithm. So they'll both have that component. And the main thing that you're replacing is you're replacing the Kalman filtering, which is going to run as fast as your software engineer can code it to. So if you have a really good software engineer that's optimizing that, that's great. They can also go a little slower, depends on your resources. What it's going to require is more GPU resources for the LSTM as opposed to the Kalman filtering. Okay.
Thank you.